As we saw in the previous video, if we were to allow the control voltage on our little simple current source to go negative, then this would force the op-amp to go into positive saturation, putting a fairly large positive voltage on the base of the transistor and forcing that base to emitter junction into reverse breakdown. Now, although you're not terribly likely to damage the transistor by doing this, this is not at all what you want to happen. So we need to find a solution to this. Do note that elsewhere in this overall series of videos, specifically in the case study videos on noise sources, we very deliberately forced a PN junction into reverse breakdown in order to generate white noise. But that's a fairly special purpose application. There are a few ways we might consider fixing the problem of the op-amp going into positive saturation. One would be to simply place a negative voltage on the non-inverting input of the op-amp, and that voltage would be more negative than any negative voltage you would anticipate on the control voltage. This, of course, does mean that instead of a virtual ground at the inverting input, you have some virtual negative voltage, which will change the amount of current coming through the resistor. Also, it doesn't really solve the problem. If the control voltage went more negative than that negative voltage you placed on the non-inverting input, the op-amp would still go into positive saturation, so you haven't really solved the problem. Another way you might consider solving the problem would be to simply add an offset to that input. Now, since the inverting input is a summing node, we can do this very simply with a resistor to some positive voltage, and of course you adjust that voltage and the resistor in order to set the total current into that summing node large enough that for the absolute most negative control voltage you would expect, that current never goes negative. This also is not really a perfect solution, since it suffers from exactly the same problem scheme number one did, which is that if the control voltage goes lower than you ever anticipated that it would, the current's going to try to reverse, and your op-amp still goes into positive saturation. So, what we need is a solution that does not have the problem of the op-amp still going into positive saturation if the input voltage goes too negative. The very simple solution to this is just to put a standard diode in parallel with the base to emitter junction, but pointing in the opposite direction. Now, if the op-amp tries to go into positive saturation, as soon as it gets just a little bit above ground, that diode begins to conduct, maintaining your virtual ground. The base to emitter junction is slightly reverse biased by about one diode drop, but in the wrong direction, and that means that it's not going to go into reverse breakdown. Also, it means that that transistor is off, so the current into your OTA will be essentially zero, and the gain will be zero. This fairly neatly solves our little problem. But before we move on, a couple more things. First, it's usually prudent to add a small capacitor in that feedback loop in order to reduce any high frequency instabilities that may occur as the op-amp tries to keep up with that virtual ground. This should probably be, with most op-amps, somewhere on the order of 50 to 100 picofarads. This scheme can also be combined with a variable offset to your summing node so that you can actually adjust the control voltage at which the current into your OTA is reduced to zero. So this would give you a variable control to change the control voltage that actually reduces the gain to zero. That can be helpful in some cases. There are other features that we could add to this, and we will probably look at a few of these in later videos. But for now we need to move on. We still have not addressed the issue of the fact that the current we set with that resistor is not quite the same as the current into the OTA. Now in many cases that's not at all a problem, but in really demanding cases it might be. So in our next video we will look at a new type of structure called a current mirror, which mostly solves that problem as well as several others that we haven't mentioned yet.